Short. Okay, great. So, all right. So we move on to a slightly different topic, which is typically a continuation only uh, from the basics. Then we move on to try and defining heat, work, and energy and its relationships and all that, right? Okay. How do you go full screen? There you go. So we will talk about heat, work, and energy, and at the end of this lecture, we'll see that all of these things are interchangeable, and these are only various forms of expression. So okay, energy and heat and work. I don't know. There's no big, there's no great, different outline that you need to make just to sectionize things. But then I hope you get an idea. So before we get into that, I think you guys might be familiar with a term called internal energy, right? And it'll be like a repetition of things, but then every material that you speak of, or see, or that exists in this universe has some form of energy, right? And when we talk about any temperature, that means it's a positive temperature, right? If there is a positive temperature, then there is some energy. And the fact that there is no negative temperature, and the fact that absolute zero is also not achieved, that means there is only positive temperature. That means every material has got some energy, some form of energy. This is such a profound truth here, right? So that it's a form of energy that going back to the microscopic idea and definition of things, you'd see that this energy actually comes from the very minute things, the atoms and molecules and their motion that actually is summed together to give you a form which is called internal energy. And that can be from the translational motions of the atoms and molecules, and rotational motions, and then there's a constant vibration because of a finite temperature. There are electronic states, electronic movements and spins and all that. There are attractions which are internuclear in nature, and then repulsions on that, and all those bindings, and because of different forces that act on the particles, all of those things put together, that gives you a form of energy which is called the internal energy. And you'd see that it actually scales with temperature. Why would it scale with temperature? Because when you're increasing temperature, you're actually increasing those vibrations, those translational motions, and all sorts of things that add to the energy form. So of course, the scale of increase with temperature are different at different times. That when you go deep into physics, and it's probably not in the domain of this class, but there's always a constant increase to the point where it kind of saturates but never decreases. There's a subtle increase it's beyond certain high temperatures, but then from extremely low temperatures to room temperatures, there's a steep increase of that. That internal energy, and yeah, and it's kind of difficult to measure the absolute value of that internal energy, right? So what we do is we kind of make a scale and make it a reference point at some point. Some sort of, let's say, what's its energy is 25 degrees Celsius, which is 298 Kelvin, and we take that as standard state, and from there, how much of energy are you adding into the system or taking out of the system? We express that as a change. So we typically express internal energy and its forms in a relative value than an absolute value. But having said that, you can actually calculate the absolute values to get a sense of what's the energy content in the material. And of course, it's not in the domain of this class. We can always go back to the ideas of equipartition of energy. When for every energy you have half kt is involved with that. I haven't made slides on that, so probably you can visualize for every half kt, and then for every degrees of freedom that you have in the body or in the entity or sort of molecule that you're talking, you can add half kt on that. So there is, I think you might have studied as to what shall be the energy of a monoatomic gas vis-a-vis diatomic gas, and then going into a little more complex things. If it's a linear molecule like carbon dioxide, vis-a-vis a bent molecule, which is like dihydrogen oxide, which is water. Water has sort of an angular shape, whereas carbon dioxide is kind of a linear shape, and they have difference in their internal energies, and those are by the factors of half kt. You can calculate that sort of H2O would have about 3 kt, and then CO2 perhaps would have about 5 by 2 kt or something. Yeah, I might be wrong, but you can do the calculations, and that depends on how many atoms are there in the molecule, and then how those atoms are placed, and so that it will give you distinct forms of vibration, distinct forms of motion that'll add energy to the system, right? So that's the microscopic form of it, and then in a macroscopic form also we measure internal energy, not quite in the absolute form, but in the relative form. And you know that this is, again, as I said, it's a function of our basic variables like pressure, temperature, and volume. And one more thing, we'll come to it more in detail later. That is, this internal energy is a function of state. That means if you do a cyclic process, you go from point 1 to point 2, and then to point 3, and then point 4, and then come back to point 1. The change in the internal energy from the earlier point 1 to the later point 1 is going to be 0. So that sort of makes a cyclic process, and its thermodynamic coordinates are supposed to be back in the same place. That's how you say that it is back in point in the point 1 in the thermodynamic space or thermodynamic coordinate space. That's a function of state. That's why we say that internal energy in a cyclic process is going to be 0. This is important because some of those properties are not a function of state, and then in the cycle, some processes are not going to come back to 0. Right. Okay, so this is one part of it. And then we think about another aspect. What is work? Right, we know what is work is, and the easiest way we define work is the force distance analogy, right? And we do a problem of defining work only with force distance analogy. That's good that we are able to define it in force distance analogy, but then it doesn't have to be restricted to that, right? And this is another way of, if you look at the what is there in the slide, it's another way of representing work. I think it's a very profound way of representing work. In that here, if you put energy into the system in a combination of molecules here inside a container, there's a movement of all of these atoms or constituents, and marked by the arrow, you'd see that those movements are fairly random. All right, this is a representation of heat. This is a representation of heat. On the contrary, if you look in the right, if you put energy into the system, all of those constituents are actually aligned in a particular direction. It's not alignment, but they're actually, the movements are in a particular direction. Right, they're going, in a proper direction. That's the difference between heat and work. That heat is there contained in the system, it's energy contained in the system, but here it is doing something useful. How sort of comfortable you are understanding this, but then see, I think many of the great professors have defined work in a way that can you raise a weight, by a pulley? A weight is there, and then a rod, a wire is connected to that, and then can you do something so that the pulley can be moved up, or the weight can be moved up through a pulley? How, it doesn't really matter how can couple the lifting of the weight with something else. As long as you're able to do that, you're doing work. This is a very engineering way of understanding work. And work for an engineer is extremely important because that's useful. We deal with energy to be able to do work. Unless you do work, there is absolutely nothing. It's only a scientific or natural process that you're observing. Whether you're not able to do something about it, the moment you're able to convert that energy or energy content or something there or something in transit into doing something useful, that'll be called work. Right? That's a philosophical definition of what work would be. But then, if you come to empirical terms, there are many other methods or formula that you calculate and compute work. Okay, so that's only a that's given only to change your viewpoint or sort of align your viewpoint in the direction of making something useful of heat. That will be called work. All right. And here in this slide, I sort of spend a couple of minutes telling you a story. All right. It's extremely important that we understand and we sort of learn the history of things, and then pay our respect to the people who have, done it, to have sort of delved deeper into difficult things, and then have come out with solutions that are so profound that they sort of are unchallenged for centuries. So here in this picture, I've kept three figures. I'm not sure if any one of you knows who these people are and then what their contributions are. I think you might be aware of what their contributions are, but then you might not be aware of who these people are. The first on the left, this person is Count Rumford. He was belonged to royalty. He was not the king, but then he was a count. He was heading a group of army people in an army base, and then his job was to bore cannons. Cannons that they're used in the battlefields and all that. And he's the person who actually first figured out that there is something in the work that we do and then the heat that's produced in a system. Okay, and this person in the middle is James Joule. I think all of you might be aware of him. Okay, and he's the person who actually convincingly figured out the equivalence of heat and work, and that's what the title is, on the mechanical equivalence of heat. And I'll tell you some stories about how he went about doing that. And the person on the right is William Thomson, contemporary people. These two are contemporary. Count Rumford is much earlier. And William Thomson is, in other words, known as Lord Kelvin, by whose name, the temperature scale is there. So the thing is that Count Rumford, while boring cannons, figured out that there is something that is we are putting into the system, when you're putting into the metal body, and then it becomes hot, and that's what he said, we're doing work in the system, it sort of increases the temperature of the body. And although there was no mathematical formulation that came out of his work, and that's towards the late part of the 17th century or 18th, what was that? 18th century, yes. And that's about 1799 and things like that. But it's not until another few days or few years that Humphrey Davy, Humphrey Davy's, does it sound a bell? Humphrey Davy's the advisor of, he's the advisor at Cambridge of Michael Faraday. Michael Faraday worked under the tutelage of Humphrey Davy. So Davy, Sir Humphrey Davy, he actually rubbed 2 blocks of ice inside an adiabatically contained wall, and he was able to melt those ices. And that's where he said that, we're able to put work into the system to be able to melt the ice. And it's not until James Joule, he did experiments. He was a brewer. He was making beer in his family business, and it was not even 20 when he started working on the boilers, and then the machines that go into the brewery. And then he figured out that there is a way we can put work into the system, and then we can, with that work we can heat up, and then we can heat up the system and get work out of it, right? He was able to figure it out, and then he presented his work in a meeting in Oxford, and then he was completely thumped down. The Royal Society people, they kind of laughed at him, say that it was such a preposterous idea that that these two are interconvertible. And it's another 2 years had passed, and it's only with the sort of what do you call that, interjection of Lord Kelvin, who was at that time William Thomson, that some people kind of took this work seriously. And then following years, after about 4 to 5 years of his first presenting the work at Oxford, uh, James Joule wrote a paper in the Royal Society, which came out in the Philosophical Transactions. That talked about the mechanical equivalence of heat. We say that we can convert work into heat and heat into work, and then he actually defined as to how certain weight can be lifted, and then the equivalence of what work can be done in the equivalent amount of temperature rise in some amount of material. So that's in the 1840s, late 40s. So from Count Rumford's observation or discovery of this equivalence from at the end of 1799 or 1800 to 1840, 1845, that took about 45 years to actually understand that, convincingly prove that heat and work are actually interchangeable. Right, so that's all for the story. So the basic definition of work in a pressure volume system is, you have a pressure, and then against that pressure you do a volume change, and that gives you PdV kind of work. Don't mind about the negative sign, we'll get into that while we do things. It's kind of a bookkeeping process. So you don't have to worry about the sign of that, right? So when there is no external pressure, then of course you would say that there's no work is done. Okay, and against constant pressure, you would see that the work done would be pretty much like the difference in volume, or the volume change multiplied by the pressure, that would give you the work done. And here it is in a graphical form. It's given in the P and V diagram, and some kind of a mechanical format would be like this. You have an expansion of the piston in a cylinder, that gives you the expanded volume, and that's the work done. Okay, and about the signs, I think when we are putting when the work is done by the system, we just take it negative. Work is done onto the system, we take it positive. It's a sort of a bookkeeping process rather than anything completely difficult or something. Just like a hisab, like what goes in, what goes out, kind of, right? So all of these things actually coming together with the formulation of the first law of thermodynamics, which is another form of the law of conservation of energy. If you say it in a way, the various forms of the first law, that's kind of confusing. But if you look at the philosophical approach of it, all of it, the startling thing is that no matter how you define the first law, it's actually giving you the same kind of conclusion every time. And some of these forms that are there in the books or in the literature, you see that the most common is perhaps the perpetual motion machine of the first kind. is not possible. It means it sort of talks about the motion machine that actually derives work without consuming fuel, without consuming any source of energy. It'll keep on working, but that would violate the law of conservation of energy. That's not possible. Uh, the second one, if you look at the internal energy of an isolated system is constant. That's another way of saying it. Okay. If the system is isolated, there'll be uh, no change in the internal energy. No heat goes into the system, no matter goes into the system. If that kind of system is there, then the internal energy will always stay put. And another working definition is that heat and work are equivalent ways of changing a system's internal energy. So the reference is the internal energy, and that means that you can change the internal energy of system by either putting heat or doing some work, or doing some work onto the system, or taking heat out of the system, and things like that. And that's the way you can change the internal energy of the system. And there are two forms, which are the mathematical form, the bulk mathematical form, and there's a differential form, which is du is dq plus dw, right? Some of you might have read in the form of dq is du plus dw, but it doesn't really matter because it's eventually a bookkeeping thing. What goes into the system, what goes out of the system. If you assign proper signs to that, either positive or a negative sign, it doesn't really matter as to what you write, plus or minus. It hardly matters. It's fine if you write dq is du plus dw, as long as the signs that you're putting are correct. So this is the simple definition I would like is that the ways, the equivalent ways of changing the internal energy of the system. Okay, and this can be heat and work, right? So and its corollaries will come to know in subsequent classes. It's as simple as it's not as simple as it looks from the outside. It's got many variations or many applications of this first law, and many different types that we will understand. Okay, now I think that there's one part we need to also understand, the concept of heat and heat capacity. All right, so if work is what we see, that to be able to do some useful stuff, or the pressure volume kind of work, what is heat? Okay, and then it says, if you go back to this, heat is the workless transfer of energy. If you work less transfer, there is no work here, and then the transfer of heat is transfer of energy itself. So it says that heat is the workless transfer of energy from one entity to another, right? Well, that's heat. But then what is heat capacity? Heat capacity is how much the temperature will change in the body if you add heat or take heat out of the system, or out of the entity, right? It means if there is a body and this, it is standardized by measuring a temperature, right? It's temperature. I put heat into the system, its temperature is going to rise, it's going to rise. How much the temperature is going to rise is going to be, it's indicative of heat capacity in the system. And these, see, if this is a body and this is a body, I add Q amount of heat here and Q amount of heat here. These two may not go to the same temperature eventually after absorbing that amount of heat that I'm supplying. Okay, that's an indication of different heat capacities. When you go to it's deep buried within its structure, it's the chemical state, the physical state, and the nature of the elements that you have present in the material, the material here as well. So that will define what the heat capacity of the material is. And then when you sort of the mathematical statement is like this is heat capacity, and this is the heat that you're putting in or out divided by the temperature difference, or what difference in temperature does it cause with the introduction of this much of heat. Okay, and in a differential form you can simply write as dq by dt. Don't mind about it. Some people write a delta q kind of, because this is not to be used in differential form, but then we are sort of neglecting that, writing simply the dq by dt. So that's called the heat capacity. And something called specific heat, or specific heat capacity, or the molar heat capacity. The difference is that the heat capacity, if you normalize that, it's like making standards, right? If you normalize that with the mole of the substance, then that will be called molar heat capacity. All right, that gives you a different idea altogether. We'll get into that later. And you normalize the heat capacity of the body with the mass of it. Then it becomes specific heat capacity. And those two are going to be useful at different points. Heat capacity, specific heat people sometimes tell, and molar heat capacity, which is normalized with every mole. Okay. Now, on top of that, you have a couple of other definitions of defining specific heat at constant volume and specific heat constant pressure. And this is what is extremely important here, in that historically, the other day I have told you, historically thermodynamics has been used to understand fluids, meaning it's used to understand liquid behavior and the behavior of gases. Right? If you look at any book, 80%, 90% of the thermodynamics books would always talk about thermodynamics of fluids. But we are understanding, or we are studying this material, this course, to be able to understand the behavior of solids, in particular metals and ceramics and polymers and things like that, right? So there has to be certain change into the way people have looked at it. Okay. So when we talk about solids, we are talking of systems, bodies and entities which are at constant pressure. Okay, that's why we need to be very much conversant with the term the specific heat at constant pressure, and that is the symbol dq by dt at constant pressure. And these are half-baked definitions. The expansion of it, or the real definition of it, is what we'll understand in subsequent classes. But it's the same thing. The heat change over a temperature window at constant volume and at constant pressure. So there are various other ways of doing work, which is what's the work done in a pressure volume system when it's going through a reversible process. Reversible processes are very efficient processes where things happen really slow. And then if you talk about the reversible process in an ideal gas system, then you would see that the PV would vary something like this. Okay, that means there is the initial pressure and the final pressure are going to be different. If you talk about this system, there's the initial pressure and final pressure are going to be are the same. It's against the constant pressure that you're seeing this expansion. On the contrary, here there is the initial pressure and the final pressure are not the same. So how do you use the constant P term, right? But then we can simply solve it in the sense that this P can be defined as nRT over V, because this is an ideal gas. You can follow the PV's nRT principle, and instead of this you put an RT over V, and the V goes inside here, and then you integrate the term dV by V, which eventually gives you nRT ln Vf by Vi. Sometimes you might have known as V2 by V1. All right, and you can also define this in the terms of pressure, and just simply do a reciprocal of that, and then with the negative sign. That gives you an idea of what's the total work done in a reversible process. That means you're trying to integrate this term, and this is a strip here. This is a strip here where you are talking about this pressure, which is only a small pressure, sort of not changing too much. Okay, and let me also tell you that here the pressure, the final pressure here and the initial pressure are wide apart. But then with every instance in the terms of the reversible process, the pressure would appear that it is not changing. So it will come from here to here. That means when the system goes from here to here, the pressure changes, but in a quasi-static manner. It'll appear that the pressure is not changing. It sort of changes very, very slowly. And then at any instance, you can define the pressure in terms of this, and for this and the volume change of dV, which is a small volume change here, you sort of integrate every strip with the pressure and the volume change. Okay, that in total gives you the nRT ln Vf by Vi. But if you do the total pressure calculations based on this block and this block and then do a negative of it, you'll see that you'll only get this much of time, right? Which is a lot lesser work than the reversible work process. So this is extremely important, that if you do the normal method of calculating work in an irreversible manner, you'll get the useful work as the rectangle here, the sort of, what is it, brown or sort of chandan colored rectangle here. All right, but when you do it in a reversible manner, the work done actually comes out to be this chandan shaded rectangular plus the peach shaded rectangle all together. So you get the total work here. So that's going to be a higher amount of work output as compared to what would have happened if you had not considered the reversible process. Instead, you'd consider the irreversible process, which is like computing the work only from the rectangle. All right. There's another way of calculating work in an adiabatic process. We'll deal with that later. Okay. Now I'll stop here by sort of introducing this one. We had talked about this earlier as well. But then see, just to okay, we're in time. We have been looking at books and everything, and there people either talk about the pressure volume work or talk about the force and displacement quantities. All right, but then in a person when we're trying to understand thermodynamics for solids, I think we need to do a generic approach to understand sort of other changes in materials with regards to a force. So I think the generalized force displacement quantities is what we should be aiming for. All right, you force displacement. I would like to say it in others the cause and effect kind of thing. Another way of looking at it is some change in a variable against a resisting force that actually would constitute work. Okay, and likewise you can find out the work done in the extension of a wire. There's a wire or something, and then you try to put a force, and that would give you a work that dW is FdL. The work done in changing the area of a surface film, you're trying to increase the area against the surface tension, as dW is gamma dA. Work done in moving a charge in a potential difference field, and then that is dW is V dZ, that's a charge, and the dZ you convert id to this VI dt. Okay, VI is, it's sort of, V is the power, and then this is dt, that's the energy unit. And work done in polarizing a dielectric solid. There's an electric field exists, and then you do some polarization, and the work done would be that against that electric field, how much of polarization are we going to take? That's measured in dW's E. That's the field into dP. There's a change in polarization of the material. And likewise, um, like you do with an electric field, you polarize. With a magnetic field, you magnetize, and the corresponding work would be mu 0 H. That's the magnetic field, and this is the permittivity, and then the amount of magnetization that you have. So, and many more such things can be added in place of work. So we have to look at the primary way of looking at it is pressure volume work or the force displacement kind of work. But then these are also similar work in a solid which can be put up in the first law of thermodynamics, right? So we'll keep it here today and take questions, um, and then continue from there on the next class. All right. So can we stop the recording? Okay, I'm stopping the recording here. We can take some questions now.